Swayam Prabha. Digital India. Educated India.
So there were a couple of things that actually came up just before we dispersed for lunch about this customer need, what is want, okay? Are we somehow driving ourselves by saying that we need something, but it's just a want that is really not necessary, but somehow we are going down that path. Very important questions, and all of us, I would encourage all of us to think about it, okay? It's not an easy question to answer. So, are we consuming too much as a society right now? I would say yes, definitely we are. And it's a scary thing if you really think about it. But what to do? What do we have as an option? There, I'm stuck. So, hopefully one of you will think of an answer as we go forward. Okay, question?
Sir, you said we are consuming too much. Wouldn't it be more accurate to say that we are consuming too much of the wrong source?
Well, we are consuming too much, then yeah, you can always fine tune the question. But at the bottom line, we are consuming too much. So, whether it's a wrong source, right source, all of that has some qualitative aspects which require a lot of discussion. We have to see who's the customer, who's going to answer the right and wrong, and so on. So, that's why I'm just leaving it for now. Yeah.
So maybe the society has been formed in such a way, like as we are advancing, that we are compelled to use more resources.
Yeah, but what does that mean? Who's compelling us and so on?
Like we have made it like that.
Or is it just human nature to want more and to consume more? Is there an aspect of, for example, competitiveness, the very competitiveness that makes us survive? Is it also the one that is going to ruin us 100 years from now? We don't know. These are all big questions, and you are the one next generation who should be thinking about them. So discuss. Right now, you may not have an answer, but it should not prevent you from discussing. Okay. So I just hope at least this 3 hours that I spend with you will fan the flame of thinking about these sort of big picture questions. Okay. Just because you are in 12th, 11th standard, 12th standard doesn't mean you shouldn't think about them. So, when you think about these questions, don't come up with an answer right away. There is probably not even an answer, but you should continue to read. As you're reading, some people you'll find convincing. Try to read the opposite point of view. And then you make a judgment about which. Whenever I read any article, especially if I find it convincing, I'll immediately look for a counter argument. Okay? And then I want to read argument, counter argument, and then in my mind see what I can do to make up. So these are all some general advice. So nothing to do with only RSIC, or maybe it has. Please take these sort of advice to heart. Okay. So let's continue on, and please, as you keep having questions, please stop. We can try to keep going forward. So as I mentioned, a systematic process is essential. So this one, I give this talk in one of my earlier first classes in engineering. So basically, I won't spend as much time as I would there, but basically, if you look at all the knowledge that we get, there's something called Bloom's taxonomy. Very interesting. It's a classification of all the things that we know, the quality of the things we know. At the very bottom, we'll just recall stuff. 3 2s are 6, 3 3s are 9, those sort of stuff which you do in LKG. But then slowly we talk about this understanding, which I already told you. I expressed some doubts about what that word means. But at least in this case, it's explaining to somebody else such that they can also do the same thing. Okay, at this point. So don't worry about the philosophical meaning of understanding, but at least being able to tell somebody else what it means such that they can also do the same thing. Then applying in a slightly unrelated fashion. So you know 3 2s are 6, but when you have 3 bags with 2 chocolates in each, being able to apply it and get the total number of chocolates is the next level of understand or the knowledge that you have. Then, so these are all the bottom of the pyramid. These are the foundations of how you learn stuff. But eventually, we want to get to these higher order knowledge, which is analyzing. Okay. So if something did not work, okay. So 3 2s are 6 and 2 3s are 6. Why? So that's a little bit higher order analysis. It's just not your multiplication tables anymore. Trying to analyze why it has to come out right. So it's a higher order skill. Then finally, the last two are what we try to train our engineering students to do, which is evaluating something. Is this good? Is it a good design or not? It's a very higher order skill. It's not that easy to do so. That means you have to be able to critique it in a very constructive fashion. You can't just say, that's not that's wrong, that's bad. You should say why it's bad. You should be able to come up with that. So that is, so literally speaking, these are the two skills that are really the most important. Maybe ChatGPT will not replace these. Okay. Everything else, already internet is taking care of a lot of this stuff, and maybe ChatGPT is doing a little bit better. GPT-4 is doing a bit better there. Okay. So this evaluating and creating. So this is where design comes in. So I just wanted to give you a feel for that. Okay. So going forward, okay. So how many of you have read Calvin and Hobbes? You like it? It's good. It's a good cartoon, right? I like it a lot. So in this case, Calvin is going with his dad and mother on vacation and goes across a bridge. And in the US, all bridges will have a load limit of 10 tons. Okay. So how do they know the load limit on bridges, Dad? They drive bigger and bigger trucks over the bridge until it breaks. Dad is always like, know-it-all kind of guy. He'll never say, I don't know the answer. He has to come up with some answer. Then they weigh the last truck and rebuild the bridge exactly the same way as before. Okay. So it has to do with our analysis and design, and also breaking things. So that's why I put it here. So, I should have guessed. The kid is very impressed. Then, of course, the mother is upset that he's talking nonsense. Okay. So basically, as we go forward, we'll try to see how does that. So this question. So how do we design stuff which do not fail, which does not fail, is what it's leading to. And so just coming back to this, and we have to do it in a very systematic process. I was telling you, rational design, a very systematic process. Let me spend a few minutes why we need this systematic process. So as I was telling you, this in the knowledge pyramid, we want to place ourselves at the top such that we are really contributing to the society. Okay. Evaluation and creation, new designs, something new, innovative. What does that mean? I know you all raised some questions. What that innovative mean? Is it just better? Is it just different? We'll answer that question also. So I'm not shying away from an answer. But design is about creating. Any design you do, you are creating something. It's creating, and creating is very difficult to do. Okay, why? It's very interesting answer. By the way, these slides are actually, with discussions of one of my colleagues, Professor Arun Srinivasa. He's a professor in Texas A&M, good friend of mine. So we have discussions like the way I make a challenge saying this is bullshit. I also keep telling him the same thing. He keeps telling me. We enjoy our, get together 5 hours of butting heads. We keep fighting about everything. Anything he says, I'll say, no, that's wrong. And then anything I say, he'll say. So anyway, these are his slides. I have to acknowledge them. Okay. They were there in the beginning of the slide, but I forgot to mention. So, so why is creation very difficult? Creating something new, why is it very difficult? Okay. So now we will slowly get to that. So what happens is, all humans, all of us, we have this, by over the years of evolution, we have this flight or fright response. You've all heard of it. If you hear a rustling in a bush beside you, 50,000 years ago, you and your cave person friend, you had your clubs and you're going for lunch, next lunch you're finding, right? And then you hear this rustling in the bushes beside you. You have to immediately decide, whether that is going to be your lunch or you are going to be its lunch. So because of that, this flight or fright response is, so our subconscious, this is a prejudice that these are all the prejudices we talk about and all, it's all well developed. In order for us to make the decision at a moment, I can't sit and calculate, oh, the frequency of the sound is this, therefore it could be an alligator. No, I can't do that. I just gotta run, or I have to take my club and start beating that fish, right? One of those two. So what happens is, because of that, we process all the information that we get into some small brackets. We try to process it, and so and that's how we operate. Even now, even if you don't like have that flight or fright response, everything we do is still based on that. That's how we are. We don't have to fight it, but we have to recognize it. Okay. So first of all, so there's a subconscious brain that makes our decisions. It always makes the decisions. So supposing I ask you, we are all going for some lunch to a restaurant. I say, what do you want to eat? Okay. You look at the menu and immediately you'll say, I want puri. Okay. Then I'll ask you, why did you choose puri? Then you will come up with some nice reasons. No. Like the reason is, last several times I ate upma or some dosa. Now I feel that therefore some difference. So you'll make up a nice story post facto. But actually the decision was made instantaneously in your brain, like that. So what happens if I ask you to make a novel, innovative pencil? Okay, all of you, I hope, have a picture of a novel, innovative pencil in your mind. How does it look? Anybody? Yes.
A normal pencil, I think, right?
No, like sound, yeah, just switch on the mic, please. So, all of you, I hope, are thinking of your own. Pencil is not a big deal, right? I mean, come on, all of you know pencils. But I want a novel, innovative pencil. So, you should have a picture. I'm going to ask you, okay? I want you to tell me what you think it is. So, he's starting to put his head out there.
A normal pencil, I'll just write novel and innovative.
No. Novel, innovative pencil. I don't want normal pencil.
Yeah, I'll write novel and innovative on it.
Oh, you'll just write it with that.
Yeah.
Okay. Fine, no problem. That's good. Off the beaten track. I like such answers. Good. But yes, please.
So it's connected to my mind, so it can write whatever I think.
Excellent. So it's a pencil that would, like, you don't have to use your hands, but it will still write. So it's still going to write. Only thing is, it's going to be connected by thought. Very nice. I like it. Yes.
The LED should be color changing.
Beautiful. Very nice. The LED should be color change. Did anybody else think of it? You also thought of it? Very nice. So you can come up with, you also thought of it. Very nice. Yes.
Like a self-sharpening pencil.
Self-sharpening pencil. Excellent. Very good. Wow. So I'm getting lots of ideas. Very nice. Yes. Oh, it has, so you can get it, like it can teleport itself from one place to another. Awesome. Because whenever I want a pencil, it's not there. So I need a pencil that will fly to my way. Okay, come on.
Pencil that can write in multiple handwritings. We can keep changing from one to another.
That's awesome. Very nice. Awesome. Very nice. Excellent.
A pencil that never gets short.
It never gets short. It always remains as long as it is. Yes.
A voice typing pen.
Voice typing or mind thought thinking. Very nice. Excellent. Good.
A lot of these ideas like color changing, self-sharpening, quote unquote self-sharpening doesn't bake. Those are just pens.
Okay.
So what makes a pencil unique?
Okay. So he's saying that such things are already there. Self-sharpening means something that doesn't change its length is a pen, is what he's saying. Something that doesn't change its thing is always. So, excellent. So, what makes it a pen? What makes it a pencil? Now, a little bit philosophical you are getting. So, excellent. Very good. So, let us try to understand, let us try to classify the solutions that you got. Okay. So, when I said innovative innovative pencil or novel pencil, okay, what kind of, let's classify what kind of solutions that you got. What were they? If you really look at it. So it is an existing pencil already, and you try to put some bells and whistles, like, it should fly, it should like ride by itself, change its, but in a sense, it's actually, so your subconscious has already thought of a pencil. It already has a pencil. On top of that, now you're putting some new bell, whistle and so on, trying to make it novel. Okay, that is what we do. That's how our brain operates. Okay, if you really want to be innovative, we have to go back and ask some of these questions. What makes a pencil a pencil? Why? What is this? So you should ask the customer. So here you didn't ask the customer, what is innovative? Why do you mean? What do you mean by innovative? You didn't even ask. You just came up with something that is flying around. I don't want something that's flying around. It costs a lot of money. I don't want, right? So you didn't even. So the point here is, so we should recognize that our subconscious will come up with a solution. I'm not denying that. Let's use it, but let's also try to make sure you're completing the design loop by engaging with the customer and finding out what they really want. That part will help us try to go back to come. So what is this novel? So for example, I give a more humorous example, which my friend Arun, Professor Arun, like he is of course comes from the US, so they have lawnmowers in the US. So he gives the same thing. How do you come up with an innovative novel lawnmower? Okay. So one person will say it should be a hovercraft. One person will say I should be able to sit there and guide it by like my pad. Okay, on my phone I should be able to guide it, or I should just switch it on like a Roomba. It should just go ahead and just have like that. They'll give all these suggestions. Okay. Finally, actually my friend says the one he had in mind was a herd of goats. Because novel in his case was he wanted a environmentally friendly lawnmower. Nothing that will. So what is the most environmentally friendly lawnmower? A herd of goats. Right? So that's sort of thing you would never think of. You'll just think of only the lawnmower and you'll add more bells and whistles to it. So anyway, so this is how we go through this process of design, and we go through this little careful process by which. So I'll just go forward. So we have the subconscious brain, and then we have this additional model making brain which comes in afterwards, and which tells us, oh, I have this nice model about why I wanted to eat puri today, not any other thing, right? So I will just go forward. I think anyway, there's not much I wanted to do here. Just wanted to leave you with a few more things about what it is, and then we'll go towards mechanics and like some. So design will have several aspects to it. I am particularly one who focuses on mechanical aspects of design, like how do you build structures. Okay, so I'm going to spend some time talking about those aspects. But before that, so I'll just go. So keep in mind, this is the point I was trying to make from the beginning. So design is not about something; it is about a customer and what they want. Okay, so it's people oriented. So. So lots of times what happens is, and it represents a way of thinking, and it can be applied to anything. That's why I asked you preparation for a vacation. How do you plan a vacation? So there you have to find out who your customers are. Your sister wants something, your dad wants something, your mother wants something, and if you want to plan something, you have to find out what they want. So what is their want and need? You have to try to identify, and you can't satisfy everything, right? You have to try to learn how to balance out what can be done and so on. So this is how you can go forward. I actually have a lot about this, but I am not going to spend too much time on it. I will just, let's see, let's spend 5 minutes basically. So one main thing is, of course, we have to make, and actually this is a very important slide because it raises some points that some of your friends asked just before going for lunch. A few people came and asked me a few points. I told them that I'll address it to their entire class afterwards. So basically, as an inventor, you can always make stuff. Okay, If you want to fly in the air, you can always tie some number of helium balloons to your chair and hope that you will fly up. But the engineer is the one who will bring them down safely. That's the very important part. Okay. So that's a very important part that you have to do. You can't just tinker your way out, because there will be real consequences on safety and so on. Okay. Now that brings me one question that one of your friends asked just before going, which was, what if a product is safe and probably even necessary for one group of people, but it will affect other people negatively? So in engineering, like engineering ethics and professional ethics is something that we spend a lot of time thinking about and grappling. And it's not an easy answer, by the way, because a lot of people have competing requirements. Just to give you an idea, nowadays everybody is thinking of electric vehicles, right? Why do people think of electric vehicles? Sorry? It's considered better for the environment, right? But is it really so? Actually, it turns out the answer is not very clear, because the lithium ion batteries are not very safe friendly. Okay, they have to be replaced, and trying to extract lithium from your mines is a very so only thing is, it's all focused, it's all concentrated in one place, so the people around will get affected, but all the cities and everything, there won't be hardly any like environmental effects. So people, the smog will be lower in densely populated areas. Who is to say that this is better than just extracting oil and all of us getting affected, right? So these are all sort of just give you a flavor of such questions. There's always these questions that should be driving us and should be driving you also. For this, you have to read a lot. Just be a voracious readers. Try to read this, that. Especially if you like one point of view, please make sure that you read an opposite point of view and try to balance in your own mind which seems more reasonable. Okay, please do that. Lots of times we tend to just read only the point of view we like, and we'll try to avoid the point of view we don't. That's become even more nowadays with all these Facebook algorithms, which will give you only your friend's circle point of view, and it'll give you suggestions which you already read, right? It's a very difficult thing. Yes, question. I'm sorry, just a little louder.
Is it better if it affects less people? Like it's the lesser of the two evils?
Isn't it better? Okay, we're really going into the ethical conundrums here. Isn't it better if it really affects fewer people? Okay, and the answer is it's not straightforward at all. How much bad effects will you allow one person to undergo if it gives benefit of some small percentage benefit to several other people? These are all questions that are very difficult to answer. Yeah, you were going to say something?
I was. I mean, if you were to just improve safety standards in mines.
Sorry?
If you were to improve safety standards in mines, the number of people working in lithium mines will definitely be less compared to people working in petrol rigs, etc. Right? And besides, the pollution doesn't affect people who are living around the people who are driving the vehicles also. Does it not count as an improvement even though it still is hurting different people?
So, yeah, I mean, that's why we are working, that's why we are not paralyzed with not doing anything right now. We are doing stuff. Because at some point in time, in some place, either by not thinking carefully about it, or by just closing our eyes to the problem, we do stuff. But if I really had to put it on paper, so if you said, look, Srikanth, you are now the dictator of the whole universe. Okay, you are allowed to make a decision between 1,000 people working in lithium mines versus like many people being affected by petrol emissions all around the globe. Make the decision. I'll be paralyzed. I will not know how to do it. I feel like I should not even affect one person badly. You understand? So it's just what we are doing right now is all these decisions that we go forward. In fact, one of your friends also raised, as an engineer, don't you feel responsible for coming up with these new products that seem pretty much useless, actually speaking, on the face of them? But you're just creating a need, the market is driving it, and so on. And because of that, there's some environmental damage, pollution, all that is happening. Right now, frankly, the answer is we are just closing our eyes and just going along with the society. Where the society goes, we go along. And there'll be some influencers who will direct the society in different ways. That's the truth. I'll be very frank there. I'm giving it to you as unvarnished as I possibly can. Okay. So the answers to these are by no means clear. I do spend a lot of time reading, discussing, arguing with friends and so on, but it's not a very clear answer. Does everybody understand where we are talking about, what we are talking about? I mean, I know you probably were expecting something in science and physics when you're going off a slight tangent, but I think sometimes these tangential things are more valuable sometimes, the kind of thoughts that they'll spark somewhere might be much more valuable. Any other questions? Okay, good. So anyway, so the point is you're trying to identify your client, making sure they're safe to use. These are all the goals and roles of an engineer. Okay. So now, so I will just. By the way, let me spend a couple of minutes. How do we go around this? I told you, right, when we say novel object, how do we make sure that we are really coming up with a novel object, not just taking something that is already there and putting some nice pink color on it and selling you as a novel object? How do we know that? So there are some very nice procedures which we teach in our first year of our engineering design curriculum. This course is called Functional and Conceptual Design. Okay, how do you take something, a customer need, and break it down into the functions? Lots of times, if I told you build a better pencil, build a novel pencil, the moment you think of a pencil, you are totally focused in a certain fashion. What we try to say is, just take what is a function, build a better writing tool. So a verb, a noun, writing tool. Don't call it a pencil anymore. Okay. Then you can make it even more abstract. Okay. So then how do you do that? You say, why do you need the writing tool? To store information or something like that. Depending on who your customer is, there will be different kinds of answers, and that will lead you to totally different thing. Okay. So finally your best answer could be a Swiss Army knife and a wooden blank. You might want to just make symbols, go back to 5,000 years ago, like hieroglyphics, and you might want to make marks on a wooden plank. We don't know. So let that be as novel, but the process is very clear. There's a nice process where you keep identifying questions. Why do you want to do this? Why do you want a better lawnmower? To cut grass. Why do you want to cut grass? Aesthetic viewpoint, like that. And why different? Why novel? Oh, I want to be environmentally friendly. Like that, if you keep asking questions again and again, you can actually identify your customer need, and then you'll be able to come up with better designs. So similarly, please apply this in your exam preparation or vacation planning, whatever you can. So why do you want to go for a vacation? Why do you want to go for a museum? Why do you want to do? You keep asking. Somebody will take a slipper and start running after you. Then you stop. Okay. Either your brother or sister will like, hey, what the hell, and start running after you. You have to stop asking questions. Understood? So you can actually apply this sort of process, and then you will find out what the core need. Then you will be able to solve it better than if you just came up with a solution and said, here it is. So that is, you suggested, right? Why can't you just ask a travel agent to do everything? The travel agent, if they're going to do it, they'll still ask you the same questions. What do you want to do? Why do you want to do it? How important is it? Keep questioning you. That's it. Okay, good. So any questions about this? Okay. So then I'm going to close this these slides, and I'm going to switch to basically what is my core kind of technical interest. What is it I do as part of my day-to-day job description? Okay, so and here is where the title of my lecture, to break or not to break, is becomes relevant. Okay, so what we do is I'm a mechanical engineer by background. So I did my bachelor's in mechanical engineering here many years ago, and so in that also, in mechanical engineering also, I've been focusing on behavior of materials. Okay, mechanical behavior of materials. So materials constitute the fundamental building block of all civilization. Materials and information. Okay, they constitute the fundamental building blocks of energy. Materials, energy, and information are the tripod, literal tripod of our civilization. In fact, that's why we call various civilizations in history by the materials they use. Do you know any examples? Bronze Age, Iron Age, Stone Age, okay, and so on. So, right, and what will be the current age now? Silicon. If you want to use a material, you have the Silicon Age, right? So, now basically, if you really look at, so you'll say there are many materials, and generally the way we use them is, of course, nowadays we use their optical properties, how light interacts with them. We use electronic properties a lot nowadays, I would say. That is really the dominant use. But still, the mechanical aspects of material use is still a very dominant aspect of. Okay? So, what does the mechanical aspect mean? I want to build a lighter car, lighter aeroplane. I want to build a turbine blade which is there inside the aircraft engine, which will not, even if there's a crack by mistake, the crack will never grow. If at all possible, it will self-heal and it will last a long time. It will never cause any danger. So, there are all of these aspects of mechanical behavior of materials that are still a very important aspect, and I work on that. Okay. So, so let me just first describe what do we mean by mechanical aspects. Okay. So, actually, if you look at it historically, of course, humans have been building stuff with huge stone blocks, right? If you see the pyramids or some of the old temples that are there in India, thousands of years, no problem. Must have experienced quite a few big earthquakes, but not a problem at all, right? So then, what's going on? How do we? What do we need to improve? What do we need to change? It turns out there's always a question: can I do that with? Can I do it faster? Can I do it cheaper? Can I do it more safely? Can I build the same building, 10-story building? Can I build it in 6 months instead of 1.5 years? Can I do it cheaper? Okay. Why do we want to do that? Why do we want cheaper? We are hoping that more people can avail of it, access it. Suppose you make a cheaper aeroplane, then there could be more flights, and therefore more people can travel to meet their friends and family, right? So there's always a drive towards making things. So now it turns out that so materials are used in different environments. For example, if you take the stable, okay, its environmental relatively benign. It will always be in within a 20-degree range in temperature. the kind of loads it's going to bear is also relatively well known. Okay, the kind of, and it's also not a critical, okay, if it breaks, if both of us decide to sit on it and it breaks also, at the most we'll knock our heads on the ground, but it will not be so critical, right? So we see such non-critical use of materials. And then as you keep going, you will start seeing materials which are critical, but in normal usages, which are, for example, the bumper of your car. You have to design it better and better, such that, you know, right now if 30 kilometers per hour accident happens, nothing happens to the thing. Can it even 80 kilometers per hour, maybe nothing can happen to. Can you design that? Those are questions. But the operating conditions are relatively benign. It's the same temperature and you know the load, so on. What force is going to act. Then there are these materials which have to be used in extreme operating conditions. Literally, if you really look at our aircraft engine in our flight, the metals used inside there, the temperatures go up to literally almost the melting point of that metal. Why? Because it turns out that if you can run the temperature at a higher temperature, it will be more efficient. Do you know what I am talking about? Have you done thermodynamics in school? Yes. Do you know what I am talking about in such a context? What about the Carnot cycle? You said the word Carnot cycle, but what about it? Why did my sentence make sense in that context? Why does efficiency increase? 1 minus T low by T high. So the T low is anyway room temperature. You cannot change that. If you make the T high higher, your Carnot efficiency goes up. So I'm quite serious. Literally right now, General Electric Research and Development, Rolls-Royce, Mitsubishi, they're all making these gas turbines and aircraft engines. They're trying to see if you can push the temperature 10 degrees more, so that the small change in efficiency that you get from that will be saving petrol for like, you know, over a year. It will save $50,000, $100,000 of fuel. You understand? So this is a constant, but if you make the temperature higher, the material will start potentially failing. Okay. So this is the broad outline of the topics which I work in. Try to see if I can design better materials or understand material behavior such that it can operate at more extreme conditions in some, or at least what are the aspects that are important. What are the aspects that are important? So generally the way it works is in a university setting, we try to ask questions at a little bit more fundamental level. Even if you are in engineering, I don't go and look at a particular alloy of steel or anything like that. I'll say what aspect of that alloy is going to make it like, you know, not fail at higher temperatures. Then the industry will actually go say, oh, this person said, you know, if you add small particles of carbides, then it'll improve strength at higher temperature. So let me see if I can make it. So there will be people who will take up such ideas from here and go. So I would say we are still, even in a university setting, we are still asking a little bit more fundamental questions and asking how things can be done and so on, more fundamentally. Okay. So my own interest is trying to understand exactly what I told you about this material behavior in more extreme environments. Okay. So what happens is, if you took any material whatsoever, it has something called a microstructure. If you really look at, all of you look at your tables in front of you, you'll see there's a wood microstructure. Yes. Do you recognize, do you see that? So basically you see wood on your list. You can see these parallel bands. That is called a microstructure. That is something that is present in the material which is smaller in scale, length scale, than your overall size of the body. So here you can see the thickness of each band is smaller than the overall thickness of the. So in materials which are not being used in common applications where nothing much will change, it's not an extreme environment, this microstructure will remain like that. I don't care. Once I know that the table is going to work, I don't care whether the microstructure is like this or whether it's got a thicker bands or thinner bands, it will not matter. Okay. However, we find that in materials which are a little bit more extreme operating conditions, this microstructure itself will change. So imagine I design a fan blade inside an aircraft engine, okay, a turbine blade it's called. So I manufacture it and then I put it for operation, but it keeps going up in temperature. There's lot of stress, air blowing against it, there's temperature varying across the thickness and all of that. Because of that, the initial how the material was formed to a later how it keeps changing. Because of that, cracks will form and there could be potential for dangerous failure. Okay. So then you'll ask the question, then how come, if things are changing, how come then we still consider flying quite safe? So what we do is, as engineers, we over design everything. So even though actually speaking, your turbine blade could be only like say a few centimeters thick in the wall, we'll make it like twice as thick, just to make sure there is no danger of any failure and crack. But that is going to have lots of consequence in the cost. So if I'm able to understand how things are happening better, then I don't have to make twice as thick. I can make it only 1.5 times as thick, and all that saving of the material will only be very useful for me. Okay. So this is the broad. So any questions about what I've talked about so far? So this is a very broad outline of the kind of things that keeps me excited in my research. Okay. So then how do we solve such problems? How do we solve such problems? So again, I want to emphasize all the maths, physics, chemistry that you're learning right now, I still use it in trying to solve this. The same equations that you're learning in school physics, I'm learning now. I'm using now and teaching to my PhD students. How? Okay. Then what is different? Yes, question. Why are you learning it right now? Huh? You're not learning it right now actually. I'm just telling you what is a big question. So if you ask what are the questions that are what is important, what drives the industry right now, I want you to be able to come up with an answer that is sort of relevant, that's all. Okay. The details we won't go through, I'll just give you a flavor. See, the thing is, lots of times if we know why we are going to learn it, where it's going to be applied, it helps us position our ideas a little bit better. I'm always a big proponent of the big picture. Okay. So if somehow we know all the stuff we're going to learn, how we are going to apply it later, I feel like we get a much better understanding of what we're doing. So, and I hope at the end of it also you will get a feel for how to what are the considerations that go into say various aspects of failure of materials and so on. This is a very interesting topic just by itself also. So how do we solve such problems? How do we even design and solve such problems is the question. So as I was telling you, we use actually school physics. Okay. So let's try to actually start solving some problems about how first we'll start with trying to design how design a leg of a table, for example. So in this process, I hope you will pick up lots of very interesting aspects of material behavior, which will stay with you for like quite long, and it will use concepts that you already learned in school. I'm not going to teach new concepts actually. You all done springs, I hope. Even if you're not, I can teach you. It's very easy. We'll only use springs to do all our calculations going forward. Okay. So yeah, question? Any questions? Okay. So basically, let us first get a feel for some numbers. Okay. So supposing, by now you would have gotten a feel for me, I'm a crazy guy. So supposing I suddenly decide that I don't want to go park my car in my garage, I want to actually hang the car from the ceiling. Okay, so I'm going to build one small structure which is hanging from the ceiling. I want to go put my car on, I'll put a ramp, I'll drive my car and put it there. I don't want because if I put it on the ground, I don't like it. I'm a crazy guy. Okay, so let me first ask you the question. Supposing supposing I make a cage. Okay, in this cage, I'm going to put my car. Okay, I'm going to drive up my car in the cage. I want to first ask the question, what should be the thickness of this wire? It will depend on the material, certainly. Okay, it will depend on the material. So one of the most common materials that we use for this will be steel, because it's damn cheap to get and so on. So what would be the thickness of a steel wire which can support my car hanging from the ceiling? Okay. Oh man, you guys all know stress and all. Huh? Okay, very good, very good. But we'll build it up slowly. What is the stress that you're talking about? Okay, force per unit area. All of you have done force per unit area in school? Oh, good. Okay, so we are ahead. So why force per unit area? Why, we only know forces, right? Why force per unit area?
If we apply a force on a body has a tendency to
Restore itself, huh?
And there's also a competing force which.
So the force itself causes the body to expand.
Mm-hmm.
And there's a competing force which causes the body to come back to normal. So that's going to be your stress and your strain.
Stress and the strain, huh?
Yeah.
Okay. No, so but still, why not talk about force and displacement instead of stress and strain? Force and restoring force. Why do we talk about stress? Right? You all learned forces. F is equal to ma and all that you learned. In the middle, suddenly they seem to have introduced something called stress, force per unit area. Why? What was the reason given to you for that?
So because when we apply forces, we apply them over a surface. We don't have point forces.
We do not have point forces.
When we apply force, we use something to apply, such as a piston, and the piston will have some surface area which interacts with our object.
Okay, good question. So you're saying like you'll never apply a point force, you apply it only an area, therefore it naturally seems, but still why force per area? Yeah, I can apply the force over area. So I'm applying, for example, my weight is there. I'm applying it over the area of my foot. But still it's my weight, that's my most important thing, right?
Sir, it's because when we're using stress, we generally want to find the dimensions of whatever we have to use. So if we use force per unit area, then from the force which we need to carry and the moduli, the Young's modulus or what are the other modulus of that steel wire, we can calculate the area of steel, cross-sectional area of the steel required directly from using stress instead of having to go roundabout way through force.
I think that's a good answer. It's definitely leading to the right direction. We'll just come back to you. One more question.
So when force acts on a unit area, we can calculate how much deformities the steel
deformation. You can calculate the deformation.
Deformation.
But still, why per unit area is the question that still doesn't remain. Yeah. Let's go to you. You have not answered. Give it to him. We'll come back to you.
It's basically like, I think, unitary method.
Like
Unitary method.
Yeah.
What does that mean? I don't know that.
Basically calculating the force that will be required for this much area,
Mhm.
and then applying it for an X amount of area. If I know for this amount of area I'll need an X force or a Y force, then for this much area I'll need X times that force.
Correct. I think you're all in the right direction, definitely, but it's maybe I'm looking for something which I'm not very clear. Let him just, we'll come back to you. Yeah.
So to take in account about the redistribution of the force that takes place, we
There's a redistribution of the force and you want to account for that. Yeah, you could, there could be redistribution, but at the end of the day, yeah, it's still, okay. Fine, let's come to it. Anybody, any other answers? Yeah. You want to switch on the mic?
So let's say a bullet has a certain force, and because it's a bullet, there's a small area of impact, right? So that might even kill you. But let's say I take a large surface area and apply the same force on you, it'll just push you. So like the effect of the force is different depending on the area.
Depends on the area. Correct. So I think all of you have it. I just we'll discuss that also. Just so it turns out, okay, the concept of stress is important in materials. So when we talk about, so first in the first school we are introduced with just forces on which we work on either point objects or rigid bodies. So I might have a rigid pen and I might apply a force on this, and you can do the mechanics. You can write F is equal to ma and T is equal to I alpha, and you can calculate the acceleration and the alpha based on that, correct? So that's what you've done. Those are rigid body mechanics or particle based mechanics is what you've done. But in engineering in real life, we work with extended bodies. There are no point bodies or no rigid body. So in that case, it turns out that we will try to first, so supposing, so in order for us to understand the behavior of material, we have to first try to find out, we have to do some experiments on the material. Okay. So all of you know the Hooke's law? Yes. So what experiment did Hooke do? Do you know? Spring, or actually he is supposed to have just taken a body, a wire, hung a mass from it. So, and kept putting plates, keep putting more and more plates and find out how much it extended. Okay. So if you look at it, this load is only W. So I can find out, and the extension is nothing but E. So he actually plotted W versus E and got some points. Put one W, one plate, got some extension. Put one more plate, got some more extension, like that. That's the first basic experiment you can do with any material. Okay, we'll come to now. This is in terms of force. This is in terms of extension only. So far, no stress, no strain, and all, nothing. This is what Hooke did, and this is what he presented. In fact, there's a very interesting story associated with it. Okay, so in Europe at the time, like slowly the scientific method was coming out, but there was also a lot of stealing of other person's ideas. People would just, lot of fraud and stealing of ideas was there. Okay, very rampant. So Hooke was, when he got this idea, of this linear extension, he was so excited about it, but he did not want to tell anybody because he said somebody will steal my idea and say, oh, I already know it. Okay, so what he wrote is his law. He wrote it in Latin, and the law is written as ut tensio sic vis. So this is a Latin law. Ut as the tension, as the force, so much the vis is life, the extension, vicissitudes, and like vis is life, say in Latin. So as the force, so much is the extension. But he didn't want to publish it. He publishes it, then people will steal it. He was really worried about it. So he wrote an anagram of this in alphabetical order. So he took the first letter, C, E, I, 3 I's are there, something like that. Just wrote it and wrote one sequence of letters and published that. Everybody's like, what the hell are you talking about? Are you like completely gone nuts? People started asking him. Then he said, okay, you don't know what I'm talking about, right? This is my law, right? Would tensor sequence. Actually, this is what happened. So people were so afraid of credit being stolen. People were rampantly so in fact, if you really look at it, in engineering and physics and so on, whatever we attribute to one person, we'll say Bernoulli's theorem, it'll be done by somebody, D'Alembert. D'Alembert's law, it'll be done by somebody else. Things are all crazy actually. I think engineers and scientists are not good at history and also rampant fraud and stealing. Okay, so literally, if you really look at it, actually boggles the mind. In fact, I'll give you just in the same context since we are all here. The solution of a quadratic equation, okay, ax squared plus bx plus c, is known for a long time. So there's a guy called Tartaglia who came up with the solution of a cubic equation. Ax cubed plus bx squared plus cx plus d is equal to 0. Okay. So very interestingly, he came up with a solution, and what he did was he kept writing out specific cubic equations. So x cubed plus 121 x plus 376 is equal to 0, and he'll write letters to various mathematicians, solve this. They didn't have a general method. They would have to keep substituting, and they'll get an answer and they'll send it to him. He'll say, yes, correct. Here, solve one more problem. So he kept giving example problems almost and irritating all the mathematicians at that point in time, because he knew the general method and nobody else. So eventually everybody recognized, oh, this guy knows the general method. They were upset with him, but they kept asking him, tell us. He said, no, this is my method. I'll keep it with myself. So then one guy called Cardano was there. Okay. So he goes to Tartaglia, and he doesn't talk about this cubic equation, nothing. He just becomes a friend. Oh, Tartaglia, you're a great guy. He talks about this, that. For 1.5 years, just the friend. Okay. So then suddenly Tartaglia himself tells Cardano, you know what? I know the solution of a cubic equation. Really? I didn't know that. Can you tell me? The guy says yes, and he tells him. Promptly, through 3 months later, there's a new book written in Europe, The Solutions of a Cubic Equation by Cardano. Tartaglia's name is not at all mentioned, right? And for several hundred years, for almost 500-600 years, everybody said solution of cubic equation is only by Cardano. Later only they found all these letters that are written to other people, and they recognized that this guy just stole it from Cardano. So anyway, bottom line, this is a very interesting science thing. So this is how he has done it, Robert Hooke. So now, if you really look at it, first things I want you to notice, I put these things, I hope you saw it's not a straight line. So never expect anything really like a straight line, okay? In experiments, it should not be anything. Somebody gives you a nice straight line, like, hey, bogus, this guy is going to sell me some lottery ticket which is never going to win, right? So you should be very clear about it. And of course, you know that there will be one at 0, 0, because if you don't apply any load, that's where you are measuring your from, okay? So the point is, it sort of looks like a straight line. So Robert Hooke, when he did this experiment, very happy that he did this. Now, supposing I ask the question, I take two wires of similar wires side by side, and I apply the same load, I do the same process to it. If I take two similar wires side by side, and I distribute the load to each of them, how will the W versus E curve look for this new case?
So are we maintaining the total thickness to be the same?
No,
or?
Two similar wires. So if I had a thickness T in one case and the same T in another case, so I've doubled the thickness. What will happen? For the same load, I'll only get half the displacement, because it's like each wire is only going to experience half the. So in other words, just from thought experiment, we don't even need to do the experiment again. We can always test it again. From thought experiment, I hope all of you are convinced that we will get a curve that will be exactly half of the, so the half the, twice, sorry, did I draw it wrong? I need to get to twice the W to get the same, sorry. I have to do twice the W to get the same extension. In order to get the same extension, I have to put 2W because each wire has to be pulled by W. Okay? So like this, every wire you give me, if you give me 3 times the thickness, it will be different wire, different load versus displacement graph. So that is why if I say, hey look, what I will do is, I will actually plot W by the area. If I plot W by the area, then even if I double the area, it will still fall on the same graph. You understand? So this is the origin of the concept of stress. That is, I can do load versus displacement, no problem at all. That is only the fundamental. But each time you give me a different thickness of wire, I'll get a different graph, because I can imagine each wire to be composed of many thin elements, each of which is supporting some part of the load. Understood? So that is why we get W area. Then I will not get many graphs. I'll only get one graph. Whether I choose area is equal to 2 square centimeters or 4 square centimeters or 3.5 square centimeters, I'll get the same thing. Understood? Now, anybody, please stop me if you don't understand. You all understand? It's just parallel springs only. It's just question of parallel springs almost. Think about it like that. Similarly, again, one more thought experiment. I make the same area, but I make it half the, or I make it twice the length, let us say. So I attach 2 strings in series. Then what will happen is, if I apply a load W, this will extend by delta. That will also extend delta. So same W will cause 2 delta extension. Right? Yeah, question? No question? Okay, like that. So basically, just by thought experiment, we can actually find out that you will get one universal curve for this material if I just consider the load by that area and the extension divided by the length. It will give me a universal curve. So now it does not matter how fat, you can be working with a big thick steel bar and you can be working with a thin steel bar, we will get exactly the same curve. Which, by the way, all of you recognize your answer. I am just explaining it in a slightly different fashion, that's all. Okay, but keep this in mind. Any questions? So this we call stress and this we call strain, and we have a curve that looks like this. Okay, that is all fine. But when I am hanging my car from the ceiling, what is my consideration? I don't want this to break and fall with a thud. So what I am looking for is my breaking. At what point is the breaking stress, breaking load or for a given. So we talk about a breaking stress. Sorry? The fracture point, the point at which, so if I take a thread and actually keep pulling it, at what point does the thread actually break?